So, welcome again to the second lecture of the course Properties of Materials, third part of Nature and Properties of Materials series, and probably the final part as well. Now, what we will discuss is, we will take up some example of again mechanical properties, just the basic stuff, and then before we move into details. So, we are talking about what basically elastic and, so if we just recap. So, we in the last lecture we just gave a few examples. Few examples which demonstrate the importance of mechanical properties, that why should which application require a material to be strong, which material require applicable material to be hard and brittle and fracture resistant, and so on and so forth. And then we looked at the difference between elastic and plastic behavior. So, essentially elastic behavior is the behavior of material. When you apply a load to a material, it gets, and when you apply to a load to a material, it may deform either in compression or in tension, but it gets back to its original dimensions when you remove the load. Okay. So, this is called as elastic behavior, which is what you generally observe with materials like rubber. It is not very visible in metals or ceramics because the deformation limit is extremely small, but it is visible in plastics or rubber, especially in elastomers and rubbers. And then you look at plastic behavior of material is when you deform it to, so let us say you have a 1 meter of material and you deform it to 1.5 meters, and when you remove the load, the 1.5 meter does not become 1 meter, it maybe comes back to 1.49 or 1.45 meters, but it does not come back to 1 meter. So, this extra deformation that you have carried out is nearly half a meter of deformation, that is essentially the plastic or permanent deformation. So, that material does not get back to its original dimensions and shape upon removal of load. So, this is the fundamental difference between the plastic and elastic behavior on a macroscopic scale. Of course, there is a lot of science behind it that we will see in the next few lectures. So, now let us other than that, there is also a difference between behavior of materials. We will get back to this dependence in details later on, but just to make you conversant with this, generally metals could be, metals are generally ductile. What we mean by ductile is they can be deformed to a shape. So, they can be deformed from one shape to another shape or one dimension to another dimension without failure at moderate loads. Now, what is moderate, what is high, what is low, that will become clear when we look at the numbers. Okay. So, metals are ductile, which means they can be deformed to a shape without failure. They are also, their strength, let us say they are also strong, but this strongness varies. Okay. So, for example, if you look at something like lead, it is not very strong. Lead deforms very easily. When you squeeze it under normal pressure, it deforms. But when you look at steel, when you apply pressure from your finger, for example, you are not able to deform it. You need to use machines to deform it. So, the strength varies, which is a function of bonding. Okay. Function of bonding. So, metals also are generally conductive. They are thermally and electrically conductive, and metals are also, they have high coefficient of thermal expansion by and large, and they are also tough and fracture resistant, which means under impact or sudden loading they do not suddenly break. So, if you drop a metal glass on floor, it does not break, but if you drop a ceramic cup or a glass cup on the floor, it breaks, it may break. So, generally metals are ductile, they can be strong. Steel is very strong, copper is strong, nickel is strong, but lead is not strong, tin is not very strong. So, it depends on their bond strength, they are generally conductive, they have high coefficient thermal expansion, they are also tough and fracture resistant, and they have lower high temperature strength. So, generally you do not use metals for high temperature applications unless it is a high melting point metal itself. In contrast, if you look at ceramics, they are brittle. Brittle means they cannot be deformed. So, ceramics cannot be converted into let me just change the spelling. Ceramics cannot be converted into another shape by deforming, just like metals. They are brittle. They are generally, they do not go plastic deformation, they generally undergo elastic deformation. So, when I said here they can be deformed, which means metal can be plastically deformed. But ceramics are generally only elastically deformed, they do not undergo plastic deformation. They generally have low coefficient thermal expansion, they have low thermal and electrical conductivity in general than metals, and they have high melting point by and large. As a result, they have better high temperature suitability, and generally they are also chemically inert. Metals on the other hand are not. We have something called as plastics or polymers. Polymers are tougher than ceramics. They may or may not be tougher than metals, but they are definitely tougher than ceramics. They can be elastically deformed and plastically deformed. So, there is a possibility of deforming plastics plastically as well as elastically. So, you can convert them into different shapes. They are lighter, but less stronger than metals, and they are also insulating in most cases, and they have low melting point. So, generally ceramic plastics are suitable for low temperature applications where you require moderate strength and moderate melting points or lower melting points. You are okay with the light thing, for example, things like buckets, etc. We use plastics, nothing else, right. And if you want to mix and match materials, what we call as then composites, you want a strong material but of light weight, then you make mixture of let us say a metal and ceramic, or mixture of polymer and ceramic, and so on and so forth. So, they are basically, they have better specific properties. Specific means per unit weight. They have better specific properties. They do not necessarily have higher strength than metals, but or higher fracture toughness than metals, but they do have better properties in terms of stiffness, per unit weight, and so on and so forth. Now, this is the general classification of materials in terms of their strength. Metals are strong, they are ductile. The strength can vary from material to material. Lead and tin are not strong, but iron and nickel are strong. They are generally very ductile, they are also fracture resistant. So, these are three mechanical properties which are very good for metals. Ceramics, on the other hand, they have lower tensile strength, they cannot be deformed, and they are brittle, and they have lower fracture toughness as well. And so, lower you can say fracture toughness, they cannot withstand impact loading. So, plastic and polymers, on the other hand, they are tougher than ceramics, but not so much tougher than metals. They can be elastically and plastically deformed, they are lighter, they have generally less strength than metals. They are also insulating and have lower melting points. Then you can make composites which are mixture of two phases, one hard and one soft, or metal and polymer, metal and ceramic, or metal or ceramic and polymer, and so on and so forth. They generally have better properties per unit weight than the individual properties. than the normal properties. Okay. So, now let us look at now mechanical the quantification of mechanical properties. So, let us first look at the concept of what we call as average stress and strain. Okay. So, so again we go back to our same picture, we have body, let us say a beam attached to a wall, we apply a load P and this body takes a different shape upon deformation, and the extension which is caused is delta. This is the original length L naught. Let me convert it black. Okay. And the final length that, so LF we can write is equal to L naught plus delta, okay, upon application of load. Okay. So upon application of load the length changes from L naught to LF to L naught plus delta. The cross sectional area AF becomes in AF, and AF is lower than A naught upon application of load. Okay. So, we define a quantity called as average linear strain So, average linear strain is defined as E, which is equal to this delta, the additional length or increase in length divided by the original length. So, basically you can say this is delta L divided by L naught or equal to LF minus L naught divided by L naught, and this is basically dimensionless. Okay. And we are saying this average linear strain, assuming that every component, every microscopic component in the beam undergoes similar level of deformation. So, this is average linear strain, which is nothing but delta divided by L naught. So, this external load that we apply, so external load is P. When you apply a load to a material, that load is resisted by what we call as internal resistance. So, this internal resistance is quantified by a property called as strength. Okay. So, when you apply load, depending upon the internal strength of the material, internal resistance of the material, which is dependent upon the bonding, it will have certain resistance. So, as a result, this P is nothing but integral of sigma into dA, where dA is the area of a small element and sigma is the stress normal to the, in this case we called as cutting plane. Okay. Now, assuming that the stress is uniformly distributed on the plane A. So, assuming that uniformly distributed on area A, whether it is correct or not, we do not, it is mostly not correct, because what we are assuming here is that each infinitesimal element or longitudinal element within the material or the beam experiences the same amount of stress. For this to happen, material must be essentially what we are saying single crystal. Okay. If it is a polycrystalline material, then different crystallographic orientations will experience different stress, because as we will see later on, stress is an anisotropic quantity. It is not an isotropic quantity, it depends upon the distance between the atoms and so on and so forth. So, if the material is polycrystalline, different grains will experience different stress because of different distances between the atoms within those planes. As a result, this is an approximation that, so as a result, in reality every element is likely to experience different stress, but to make it simple we assume that stress is uniformly distributed. So, essentially basically we can say in a polycrystalline material, stress on each, let us say, grain. I think you know the difference between the grains, because grain is a is a part of material, is going to be different because of changes in orientation of grains. So, some grains are going to have this distance between the atoms. So, this is, let us say, grain 1. In other grain, the distance between this, so as a result the bond strength will be this. So, this could be grain 2. So, as a result the stress which is going to be experienced by different grains will be different. But let us say for the sake of assumption that the stress is uniformly distributed on area A, which means sigma is constant. If sigma is constant, then we can write this P as sigma into integral of dA, and if A, this can be again approximated to A, then this P becomes sigma is equal to A, or sigma becomes P divided by A. This is your average stress. In reality, stress will not be uniform because of anisotropy of stress in materials, and stress is an isotropic property. An isotropic quantity, but we are assuming that here it is uniform. So, for average stress and strain below elastic limit, let us say below elastic limit means there is no plaster deformation that happens. So, when you increase the strength increase the length from L0 to LF, and when you remove the load, the LF comes back to L0, which means LF comes back to L0 upon removal of load. Under those conditions, Hooke's law is valid, which can be applied to sigma is equal to epsilon into E, and this E is the proportionality constant, which is called as modulus of So, when you write this equation in the scalar form, the E is also a averaged out quantity. The sigma is average, epsilon is average, as a result the E is also the averaged out quantity. However, on a microscopic scale, both stress and strain, they are tensors, which means they are direction dependent. So, here we said that it is an average stress, average strain on a plane. Every element faces the same stress, as a result you average out the stress, but in reality stress and strains are microscopically speaking, they are tensorial or vectorial quantities, and as a result there is a direction dependence or their anisotropic properties. So, what do we now mean by these stress and strain tensors? So, before we get into that, let us look at what tensors are. So, tensors basically you can say tensors are defined by this formula 3 to the power n, the number of components which are going to So, tensor is basically you can say a matrix. Okay. So, if n is equal to 0, then it has tensor has one component. So, one component will mean that quantity is scalar. Okay. But when n is equal to 1, then it has 3 components, which means the quantity is vector in nature. And when n is equal to 2, then it has 9 components, and then it becomes what we call as a tensor, and this is tensor of second rank. This, so n here is nothing but the rank of a tensor. So, a first rank tensor is vector, 0th rank tensor is a scalar, and second rank tensor is a matrix of 9 components. So, you can keep adding, increasing the value of n. So, when n goes to 3, it will have 27 components. So, it is a tensor of third rank. N is equal to 4th will mean it has 81 components, and it is a tensor of 4th rank, and so on and so forth. So, life is generally lucky that we do not have so many components in reality because of thermodynamic and material symmetry considerations of in most quantities. But so, as far as stress and strain are concerned, strain is a tensor of, strain is depicted by the notation epsilon ij. So, where I and j are integers going from 1 to 3. So, I and j can vary 1 to 3. So, as a result, this epsilon ij is a second rank tensor, and it has, which means 9 components. So, if you write this epsilon ij, this will become epsilon 1 1, epsilon 1 2, epsilon 1 3, this is your strain tensor, and it has, because of symmetry of strain and stress, it does not actually has 9 component, it has 6 components because of sigma epsilon ij being equivalent to epsilon ji. So, as a result, for example, which means epsilon 1 3 will become epsilon 3 1, epsilon 2 1 will be equivalent to epsilon 1 2, epsilon 2 3 will be equivalent to epsilon 3 2. So, as a result, you will reduce this to 6 components because of symmetry. Okay. This is about the strain. So, the stress can be written as sigma ij, and again you can write this as sigma 1 1, sigma 1 2, sigma 1 3, sigma 1 1, 2 1 2 2, sigma 2 3, 3 1, 3 2 and 3 3. Again sigma ij is equal to sigma ji. So, this will essentially have 6 independent components. So, here it shows 9 components, and now within the elastic limit, you can write, or instead I can write sigma ij is equal to epsilon, let us say KL, and then the proportionality factor is essentially E ij KL. So, this ij, E ij KL is essentially, we can say, modulus or stiffness, which is essentially 4th rank tensor. And this will have 81 components. Now, 81 independent components, however, because of symmetry and other things the number of components go down. So, we do not really have to, we are not that unfortunate, and you can also relate accordingly stress, strain with the stress So, you can write this S I j k l, this is called as elastic compliance, and this is again a 4th rank tensor. Now, here we can see that strain is dimensionless, stress has a unit which is Newton per meter square. So, as a result the modulus, or I can write K L, this will again be in Newton per meter square. So, this is the correlation that we have. So, if you now combine these two quantities, so we can say that we have written one for the elastic compliance and another for the modulus stiffness. If you combine the two, we can write them as E I j k l into S k l m n is equal to S I j k l and E k l m n, and this is basically equal to delta I m into delta j n, and this delta is called as chronicle delta. So, this delta I m is equal to 1 when, so this is because of the property of matrix, and you can see the two relations should be compliable with each other. So, when I is equal to m, delta I m is equal to 1, and when I is not equal to m, this is equal to 0. Similarly, delta j n is equal to 1 when j is equal to 1 and 0 when j is not equal to n. So, for this equation to hold true, because these two equations can be inversed, as a result this property must be obeyed as far as vectorial notations are concerned. So, we will stop here. What we have done is we have looked at the what is strain and what is stress, what is average stress, what is average strain, average modulus, considering that stress is uniform. However, in reality stress and strain both are anisotropic properties, they vary in different materials in different directions because of properties of materials, and we have looked at the equations how they are represented in vectorial form. So, we will do more analysis of these elastic properties in details in the next class. Thank you.